Welcome back to uh, our system skill class, and today is basically the last topic we'll cover. In the assignment, I think there's two parts. Part two instruction may be incomplete. Let me know after the lecture ends on that, just in case, because it might be the case that the latex has some bugs, and I did not see that. All right. So basically, let's can you either put it on Skill text on Discord and I'll fix that because I might have some error on the LaTeX uh, uh, file that I try to compile, so it doesn't really generate the rest of the spec. I'm so sorry. All right, and today we'll cover like as I said, is last topic for this semester. It's called virtual memory. Anyone heard about this word before? Virtual memory. Anyone? All right. It is actually something that a lot of people might have heard, right? And you actually all have been using them without noticing. Uh, how are you with using pointers? What is a pointer actually? What is a pointer? What does it store? The pointer that we've been using in A3. It store an address, right? So how many of you think that the address is going to be my, okay, you just answered it. So the address we've been using is actually virtual memory address. And what does the word virtual mean? What does the word virtual mean? It's not real, right? It's actually not the real location or simulated location. It's more like a some location that I would know what they are, right? It's kind of like when I try to point to a location in the real world, right? Let's say I give you an address. How many of you have a nickname with your address? Something like your friend's house or uh, like Garan's house or John's house or Meta's house, right? You can give nickname to an address. And if you know the real location, if you know the mapping between the nickname of an address to the real location, then you can find the actual house, right? So basically, you can basically have a nickname, right, for something that has a mapping for the real location, right? And we do this a lot. We give it a nickname. We give a lot of place the nickname, right? Like Mahidol Salaya campus, right? If I give the word Mahidol Salaya campus to some random people, they might not know where exactly they are, or like the university is, until you give them the actual address, right? Which actually I don't know. So I guess that's a bad example. But regardless of that, virtual memory works the same way. But at this point, you might be wondering, like, why do we need it, right? How many people question the existence of virtual memory? Like, why do I need one? So to answer that, let me kind of give you a motivation on why we need this. So from a programmer point of view, right? Programmers see an abstraction of the memory. It's like unlimited, right? It's contiguous. How many people think that, hey, whenever I malloc, there's actual physical DRAM where I'm allocating the memory from? So what if my memory is full? All right, how many people have like 20 or 30 different Chrome tab opening and suddenly your computer gets slower? Is it because your memory is full? I'm pretty sure you guys all experienced this, right? Well, it is a PC with not a lot of spec, right? And one of the important spec for your PC is the size of memory, right? How many people have a laptop or used to own a laptop with only like maybe 4 GB of memory? If you use a laptop like that, right, and somehow, yeah, those painful days, so things are gonna become slow, right? So, but let me ask this: does it actually crash things? In that case, does it doesn't crash my computer, right? It's not like suddenly I cannot run a program. Because imagine this: if you call a malloc and it say, "Hey, I don't have enough memory," what would happen to your program? You're writing an application, right, and you use malloc, and then suddenly your malloc returns null, which it can. Basically, if malloc returns null, it means that I cannot allocate anything for you. But imagine in a real application and you run your computer normally. Does it? What do you do in that case? What do you do? Right? Does the Windows OS or Mac OS keep letting you opening the new program and somehow they manage, right? That's because you have virtual memory. Give you this notion that you have unlimited memory, right? You can somehow cook up new space out of nowhere, even though DRAM is full. Like even though whatever you have on your computer is totally full. Also, think about having two programs running at the same time, with one program making malloc and free, the other program also keeping malloc and free, right? But from the Mac OS and Windows point of view, what if I just do malloc and free, malloc free, malloc free, malloc and free? What would that make my DRAM look like? Would it be a pain, right? If I write my program, I have to be careful that someone would suddenly free my own whatever I malloc. Would that be a pain? How many people hate segfault? At this point, I think everyone hates segfault. All right. So if you love segfault, you're basically you're basically being sad. Basically, imagine you write a program which is correct, but then somehow the other program that you run with can cost you a segfault. Would that be a pain? Would that be something like I don't even want to be a programmer anymore in that case because I don't even have any guarantee on anything. That's something that could have happened, right? If you don't have virtual memory, because what the OS give you, what the operating system like Linux and Windows and Mac OS give you is it has a notion of how to build this virtual world around your program and work together to give you this illusion of I have unlimited memory. Everything is contiguous. I have a big chunk of free land where I would be able to walk around, access my data, and as long as I call malloc properly, and as long as I access the location that I own, I'll be fine, right? But inside the hardware, everything is physical, right? Your DRAM is a physical thing. So now what exactly is virtual memory, right? I have this slide that kind of try to do the explanation, right? So let me first explain that and I'll have an analogy on what does this really look like, right? So basically every single address you're using is going to be associated with a location somewhere in DRAM, right? So the process, right? If going back to your Linux lecture, we have program and process, right? Process is basically whenever you double click the program and it's running, they would have its view of their own memory address. Things like the pointer you're using in a program, right? These are virtual address. And the computer system and the hardware would create this mapping between virtual address and the physical address. So I'll write VA for virtual address and PA for physical address. Basically, what I'm saying here is there's a mapping between VA into PA. This is a mapping. And today we'll figure out what is our mapping and how do I figure out if I have my virtual address, how can I get the physical address? Because if you want to write a functioning OS like Windows or Linux or Mac OS, you need to be be able to maintain these things, these mapping. But the thing is, there's an element in hardware called the memory management unit that manage the translation between the virtual address to the physical address. So this is similar to when I have a nickname for my location in Google Map, right? I can have the location, as I said, your friend's house or my parents' house or my work university, right? That's the nickname. And then think of it as those are the virtual address. And then the mapping is basically I would have the real address becoming the physical address so that I can go to the location given the nickname, right? So the benefit of this is, first of all, every single application would see their own virtual space. I don't have to worry about everyone else's address. I have my own address and that's it. Thus, the OS makes the MMU. The OS kind of work together with the hardware MMU. But if you want, you can kind of like do everything in software as well, right? These are design options depending on what you want, right? If you want to design everything in software, you get the flexibility, but it's going to be slow because these are programs, so you need to run them on a CPU. Or you can also do everything in the hardware, right? And in modern day processor, they come with the MMU. They can do the translation for you, but the OS would maintain the mapping. So the OS know where they are. The OS has the map. Think of it that this way. The OS has the map, so I know where each of these things are. And because the OS has the kernel privilege, right? It knows about every single location from the OS point of view. It can access every location, which means that I'm good because the OS control every single application that I'm running, right? But from the user space, when I run an application, I can only see my own address. So this gives a good illusion that I just see my own space and that's all, right? Second benefit coming from that is because I only see my own address, I got memory protection. Why are they good? It means that some random program cannot modify my data. Why is that good? Why is it good that I can provide memory protection, which is basically guaranteeing that no random program can modify my data unless they have the permission to do so. Why is that good? It actually does not protect just memory leaks, but it also prevents them from changing my data, right? It protects my data from some random undefined behavior from a potential attacker like a virus or security problem, right? It can protect from not well, is it data corruption? It's more like someone else attacking my data. Because I write, let's say I write the anyone remember assignment 3, the determinant equation from the matrix determinant, right? Is that assignment 2 or 3? I forgot. Sorry. A3, right? Imagine you are basically trying to solve your question and I have this random program changing your results. What would make you feel if I do that, right? So memory protection prevent any random program from doing this. It gives you the guarantee that inside the software no one can do that, right? No one can do that unless there's bugs in the OS or there's a bug in the kernel code or like it's like unless it's like a huge bug somewhere, you cannot modify someone else's data, and that's a good thing. And also that's why you got segfault, right? Because essentially what's segfault? What is a segfault? Or what is a core dump? It's illegal access, right? And illegal access is that. It's like you cannot just go walk into your neighbor's house and change things. That's just plain illegal, right? You can't do that. In computer, same things here. my own virtual space is my house. No one should be able to come in and change my data, right? So that's the benefit of virtual memory. So these are the two of the key benefits. Then the other benefit is you can also have unlimited memory, but you might be questioning like, but I have limited DRAM, right? I have limited DRAM. So what do I do when I need more memory than I actually have, right? Let's say I have a 4 GB laptop, and I was trying to find like learning material for how to use GDB, and I was opening like 30 different Chrome tabs, including PDF reader, including some YouTube channel trying to teach me how to use GDB, including, I don't know, like basically a bunch of things, right? And then you run out of memory. As you said, it doesn't really crash your computer, it's just making slower, right? Technically, virtual memory gives you this limited area, but there's way to create this illusion. What's the next level of your scratch space where you can put data in from your memory? What's the next location you can go to? And that's a really big space. You can just put a lot of data in there. You run out of things in your DRAM. Where's the next open space you can use? Hard drive, right? Hard drive. So one thing that virtual memory give you is I can also map, quote unquote, right, to the hard drive. It's not now when you go to the hard drive, it's not like a direct map anymore. There's like a lot of process trigger when you have to actually get the data from the hard drive. So that when you run out of memory, that's why things are really slow, because these are a slow thing. But that's the third benefit. Virtual address can be mapped to a much bigger space. And that can be done through the page table structure. When the hard drive also get filled up, um, that so basically when like most of the time the OS would kind of configure how much, like how many gigabyte will be dedicated for this space. Most of the time, the user would cry that it's too slow and you reboot the machine before this thing get filled up, because once you reach the boundary between, like, let's say I have like 16 gigabyte in the hard drive, your computer is going to get really, 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 really slow. Does the data stays in the hard drive forever? That's a great question. So let me finish up this one slide first, and we go to that discussion. That's a great question. Um, so the page table structure doesn't enable just benefit three. It enable every single benefit. All the three benefit: memory protection, the mapping that I have the virtual space of my own, and the fact that I can make it look like it's a much bigger space. That is done through the page table structure, right? Now let's go to the question from the chat that asks, right? In that case, does the data stays in the hard drive forever? And the reason why you ask this, you might notice, right? If I have a file in a hard drive, it's gonna stay there. But what's different about the memory? So if I turn off my machine, what would happen to my data? What would happen to my data if I turn off the computer? The data is gone, right? The reason why the data is gone is actually DRAM is called volatile storage. What does volatile storage mean? It means that I lose data over time. I lose data over time. And the reason behind that is DRAM use one transistor, one capacitor. This is where you store the data. And anyone remember what is a property of capacitor? Anyone take like a, I guess, intro to electrical engineering? Like, what's the property of the capacitor to store electron? This thing lose electron over time. Basically, it means that if I turn off the computer, which means I'm not supplying the power anymore, I lose my data in the memory, right? But what about whatever I fill inside the hard disk? Whatever is in there? Well, there's multiple things you can do. Basically, you can make it gone. You can just unmap, right? Because if you don't map them anymore, you don't know what are these data, so there's no use to it anymore. So maybe they would stay in the hard drive forever, but because I don't have the mapping anymore, when I boot up the machine again, I can just map new data on top of it, and that's going to be fine. That's the same as when you delete a file, actually, because when let's say you delete some file, do you know they don't actually remove the file? They just get rid of the mapping between like file icon, like you don't have the mapping to that location for the file anymore, and that's all. Would the computer just mark that region as unmapped? Why does sometimes if things are unmapped, why does sometimes it take a lot of time? So that's another great question. I love you guys. Um, so it depends on multiple factors, right? Sometimes when you do the unmapping, you need to also update the structure because to maintain the mapping, you need some structure, right? To map the file, right? So sometimes removing can take more time. But you might have noticed when you delete things, it's actually much faster than things like copying file, right? So these things keep getting unmapped and remapped again. It just keep getting unmapped and remapped again. Sometimes when you unmap, also the machine can do something like compaction because if you keep, let's say this is your whatever space you're using, right? And then these are allocated, right? Let's say these are allocated. But suddenly, right? Suddenly I do the unmap. So anything in blue is unmapped. I unmap this part, I unmap this part, I unmap this part, I unmap this part, I unmap this part. What does my thing look like now? It's a bunch of like holes everywhere, right? So if I want to make a contiguous chunk of things so that the next time I remap, I have more space, right? Then I also, when I unmap now, in this case, I need to kind of move the data around to reorganize and pack things over, right? And that's when sometime when you do the, I guess, quote unquote unmap and remap, which is some like deleting file or get rid of data or free things. It can take some time to reorganize these as well, right? That depends on multiple factors. It also depends on how the OS manage, right? It also depends on how the OS manage these locations as well. There are certain organizations that allow you to manage it in a more efficient manner, right? And that's why people keep working in things like storage systems, like how can I even manage the file in a faster fashion, right? Through changing the kernel and changing the system software so that we can do a better job at like mapping and remapping. All right, so hopefully these are more clear. And again, sorry for being sidetracked, but these are great questions. All right. So now let me go through the new terminology, a page. What is a page? What do I use a page for in real life? So let's say I have a page of paper. What can I use it for? True. You can use paper airplanes. Awesome. I love you guys. To write up something, right? Write things on it. Put letters on it. Think of letters as your data. I can put data in a page. And let's say I have a book, right? What does it tell when I say go to page 32 of the book? it basically means that look for the page 32, is something written there, there's some data over there, right? So a page in DRAM kind of works in a similar fashion, right? A page is just a range of address, right? It starts from the first page to the last page. Every page has an ID, an identifier. It can be number 0, number 1, number 1024, number 1003, number 10,232, something along that line, right? It's just the number of the page tag to whatever data goes to that page. When you look at the CPU, the size of the page for most computing system is 4 kilobytes. Uh, it can be any size, to be honest. And if you buy a computer nowadays, just would happen that yes, they are divided equally. Every single pages will be 4 kilobytes in the system that you're using right now. But there are also ideas on how to make a bigger page of like 2 megabytes or even 1 gigabyte page, right? We are not going to discuss the trade-off. That's a little bit more of an advanced topic once you know how the system works and once you know how do I get performance out of it and what's the downside from a much bigger page, right? And a page is mapped somewhere in DRAM. And the program you see will have the virtual address, which means that you can see virtual page. Basically, you have virtual address and you have the virtual page number. So this is the virtual page ID. When you map to the physical address, it will belong to a physical page. So physical address also has its own physical page. We call this physical page number. Right? Physical page number, which is basically is an ID again for your physical page, right? So when you have the virtual address and you translate that to the physical address, basically the operation is you change the virtual page number into the physical page number. You change the virtual page number into the physical page number, and we'll talk about how to do that in a bit. This is the magic of indirection. Anyone heard about this terminology, indirection? What does indirection suggest? What does the word indirection suggest to you? It's not direct, right? So anyone have ever played like a treasure hunting game where you start with a clue and the clue would point somewhere and you go to that place, you find the next clue. Anyone played these kind of games before? Where you start with one clue and you follow the clue to go to the next location, then you find the next clue which points to the next location until you find treasure. Right? You flashback. Sure. Same process. You start with the first clue. You follow the clue until you found the treasure. The treasure is your physical address. You start with the virtual address. So if I have the virtual page that maps to the physical page, right? And let's say there are so many virtual pages right now. And if I slice DRAM into multiple pieces, it's still less than virtual pages, right? So first problem is, well, how do I tell where's the physical location of my virtual page? Now I can solve this with a page table. So what is a table? What does the table do? What can I do with the table? Can I store some mapping between a virtual page number? It has rows and columns, right? So one thing I can do is I would store virtual page number and I pair that up with a physical page number. Actually, basically I have a map. The input is a virtual page number and somehow the table store my physical page number. Can I do that? That's called indirection, basically. So I can have a table that store the location of the page. For example, I can have a table that looks like this, right? The left side is my VPN, the right side is my PPN, right? So let's say I have the VPN of 10. It means that if I have VPN of 10, you go to physical page 22, VPN of 11, go to physical page 32, VPN of 12, go to physical page 8, VPN of 13, go to physical page 197, 93, just random number, I'm sorry. Virtual page 14, you go to 1020, right? This can be something that's feasible, right? I have a table. It does look like a cache where the VPN becomes the tag, right? And PPM is your data, but it's a little bit different in the sense that you have one number and you spit out another number, right? And that's the concept of the page table, right? So one thing I can have is I can have my clue that point to the treasure. That means my table is one level. I use my VPN. I got the physical page number and done, right? One table. So that's an easy treasure hunting game, right? I can also make this more complex by adding the next level. I have the first clue would give you the location of the second clue, right? So first clue, give location of the second clue, give location of the third clue, give location of the fourth clue, which gives me location of my physical address. So I can have that, right? So that's basically the page table structure, right? We call each row here page table entry, because essentially these are the entry in my page table, like row 1, row 2, row 3, right? And when I point to the next location, I just point to the beginning of the table, so I can use some way to go into, okay, what number of entry am I accessing, right? Now, does this seem simple, to be honest? Like, this is a simple structure, right? I have my inputs, it spits out my output. It's actually really simple. And in your CPU, you ended up going through this 4 times. So basically, you have the first clue to the second clue to the third clue to the fourth clue. Afterward, you get your physical address, right? So here's a page table structure. What goes in it, right? So now let's see what goes in it. Each process has their own page tables, right? Or is it a page table that's used for the entire machine? The entire machine has the one page table shared by multiple processes. But in there, so let me show you the page table structure because it would give you the answer to that. This is the page table structure, right? You have the row over here, row of PTE, page table entries, right? So basically a bunch of page table entry. So this whole thing is a PTE actually. So one bug on my slides here is PTE 0 is actually the entire row, but part of the PTE is a status bit. So this thing will tell you like who owns this page. Things like, is it read only? Is it from the user? Or is it kernel? Is it last used? So these things are information that you can add to the page table, right? Things like who owns the page, we call this address space ID. So let's say I have a program with an ID 10 and I go through my page table and in the status bit, the ID is 5. It doesn't match. What will the OS do in that case? I have an address, I have the virtual address, so basically I have a pointer, star P, right? This is an address. And your program over here, your program address space. Address space is basically the ID for the virtual address of your program. Let's say the ID is 10, right? Some address, but when you go look at the page table, the address space ID this is ASID or address space ID, turns out to be 5. What does it mean? What does that mean to the value of my pointer? My pointer now holds an address, but it doesn't belong to my address space. What does it mean? So let me boil down to a simple question. Yes, segfault. That's why you get segfault. Because the address you're trying to access, you look up the page table and then the OS is like, why does the address space ID does not match? That doesn't belong to you. That thing doesn't belong to you. So let me segfault and kill your program. Right? So hopefully that answer, like basically the OS maintain the page table. Why does the OS should be the one maintaining the page table? Because it's kind of like a manager to see everyone's status who owns, right? I cannot have my program seeing someone else's data status on where's the data in the DRAM because I can then access it, which means I violate memory protection, right? To maintain memory protection, these are handled by the OS because everyone should be able to trust the OS, well, at least to some extent, right? So now let's break down the virtual address. So if you look at virtual address, right, there are different parts of the virtual address. The lower bits, we call this page offset. The way this works is similar to our byte and block bit from our caching lecture. So what does the byte in block bit do? What does the byte in block bit do? It tells you the exact byte that you're trying to access, right? The exact byte you're trying to access. So if I ask the same question, what is the purpose of my page offset? I have an address, certain parts of it will be the page offset. So what does that do? It tells me the exact byte on the page that my address try to access, right? So the next set of bits I use as an index to the page table. So let's say this is my virtual address. Virtual address, right? The lowest bit we'll call this page offset. This is the virtual page number. And as I said, we use this to index into the page table. All right. So if I have a 4 kilobyte page, which means that every single page on my machine is 4 kilobytes, what should be the bits for my page offset? How many bits are in the page offset? Let's also assume that I should be able to access every single byte on my page. So what would be the number of bits in my page offset? Log 2 of 4K, which is 12 bits, right? Then I can access every single byte. But let's say now I can somehow I don't have to access every single byte. I just need to be able to access every 4 bytes. Yeah, it's not 4K over 8 and log 2 of that because in that case, it means that your address will skip every 8 bytes, right? So basically, this will tell you the finest granularity, like how fine grained you want to be able to access each pieces of your data. If you want your address to be able to access every single byte, then you do log4 of the page size, right? But that can be modified based on the system and also the hardware specification. Generally, if you want to make sure you can access every single byte, then it's log of the page size. Now, let's say you have the virtual address now, right? As I said, you have page table entry and the page offset, This is virtual page number. It tells which row you are accessing. So as I said, this entire thing is page table entry. Again, sorry about the confusion. I said PTE0, PTE1, it's actually the entire row. This part, we call this physical page number. Physical page number. So you use PTE to figure out what row you go to. So let's say PTE is, let's say PTE equals, I don't know, 3. The whatever numbers in here is just a bunch of 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1. What row am I accessing here? PTE turns out to be a bunch of 0 ending with 1, 1. Translate that to a decimal number is 3. So what row am I trying to access here? It's this row, right? The 4th row, which has the PTE3. I go there, I check what's my PPN. Then my physical address is going to be PPN, right? And I take the page offset. And that's it. That's my address. That's the physical location in DRAM. I just take PPN, I plug in the page offset, I'm done. Is this simple? So let me ask you this. Then does this give me memory protection? Does this give me memory protection? Yes, because I have the status bit right here, right? This thing would check for access violation. So we now have memory protection. We also have the ability to have whatever virtual page number, because as long as I have the ability to go back to my table and I can tell the PPN, I'm good. Right? Now, what does PT3 tell us? It's just a bit, a series of bits, which is a number. It tells us that is the location, so imagine DRAM is a book. Imagine DRAM is a book. Each page in the book is a page in DRAM. PTE is telling you what page you have to flip to in order to find your data. It's more clear. Imagine the whole DRAM is a book that has lots and lots and lots and lots of pages. To find your data, you need to find what? What page does the data located in, right? But you don't have the physical page number. You have the virtual page number. And inside the book, it uses the physical page number. So you first go to this table to figure out if I have VPN of 3, what is the PTE? PTE can be 1078. It means that you flip to the page 1078 in the VRAM book, then you plug in the offset to tell what character in the book on the page you are trying to access. So now is it more clear? Is it more clear? Or is it now even more confusing? Let me know, because this is the part that can confuse most of the people. All right, awesome. So if you got it, great. If any one of you still are not sure what's going on, so now let's go through some more example, right? Actually, how about this? Since it's almost 3 o'clock, let's take a break. We'll come back at 3 o'clock. Let's chew down this a little bit before we go through the 32-bit x86 example before we then go to the 64-bit example. All right. So now let's take a quick break. If you have any questions, feel free to basically take some time to type in the questions. You can send me a private message. I won't tell the class who you are. I'll just tell the question getting asked, and we'll come back. We'll address all the questions in case anything here is confusing. All right. And we will be back at 3. So we have a 5 minutes break. All right, so now we are back. The VPN look at the page table. Yes, the VPN look at the page table. The page table is basically give you the mapping between VPN to either the next table or the physical page number or PBN. So when I said it can go also point to the next table, that's basically what the 32-bit version of the x86 do, right? So in the page table in x86, and to be honest, any modern CPU architecture has a tree-like structure. What does tree-like mean? Basically, it means I start from the top, right? It goes down multiple level. And the lowest level here is where you can find the physical address, right? So basically that's what tree-like mean. All these page tables are stored in memory. In the 64-bit, whatever you buy nowadays in the CPU, we'll have 4 levels of the page table where the root points to the location of the first level. The virtual address and parts of the first level structure would point to the second level. So that's basically you got a clue from your virtual address. You then find the first location to get the next clue from the first level structure, and you keep following that until you find the page table, the last level of the page table before you go to the physical address. And each page table will store the page table entry that behave like a tag to provide the information on where is the next table located. When you go through this process, when you go through this treasure hunting process, we call this a page walk. When you perform a page walk, you go through the page table structure from one level to another level. What do they mean? So let's go with the 32-bit first. We have 2 levels of the page table. Each table contains multiple entries, and the status bit will store, first of all, the pointer to the next table, and a bunch of special bits like is there a data there? Is read or write? Who is it? User or supervisors? Things like when is the last time I accessed or have I ever accessed the page? Is it a global page? Any extra bits like address space ID, who owns the page table, and things like that, right? And when I do the page walk, as I said, let's assume 4K page size, 2 level of the page table. So my page offset is going to be the last 12 bits. Virtual address is 32 bits, so it means that if I use the last 12 bits for my offset, right over here, my address, which in this case is a virtual address, is 32 bits. It means that page offset is 12 bits. And the remaining 20 bits are for the virtual page number. I have 20 bits left. I need to crack 2 levels of the page table. So what makes sense, I would divide them into 10 bits each. So here's your virtual address. This is 12 bits. This is 10 bits. This is 10 bits. The first level, if you read a textbook, that talks about the 32-bit x86, these are called the page directory. When we go to 4 levels, like the normal CPU we use nowadays, we don't use the name page directory anymore. There's actually, we can't just go with like level 1, level 2, level 3, and level 4, because now there are multiple levels. But if you read textbook that talks about 32-bit version that are a little bit older, they will call this a page directory. And then the page directory, as I mentioned, there's multiple row in the table, right? So let's say the index bit here is 00000000011. Now, what is that number? 3, right? So in that case, we go to row with the number 3 in there. This thing tell me the next location of the page table is an address. Basically, treat this as a pointer. So let's say this address is 0x what? Give me some number. 0x 070000. So that's my address. It basically means that now the next level is another table, right? Then the next level is another table. This thing starts at 0x70000, right? Basically, you store the address where my PTE3 points to. That's the first line in the table. So now, let's say the second level index is 00000000100. What's that number? 4, right? So that's number 4. So what row am I going to? What PTE number am I trying to access here? PTE 4. So I'll take a look at this row, right? And try to figure out, okay, what's the number that goes in here, in this part? The number that goes into this part, right? So let's say this number is 0x, let's say I'm hungry, 0x beef, B-E-E-F. 0x beef is inside that PTE4, right? What is my physical address? So let's assume page offset over here is 12 bit. Can someone give me a random 12 bits number? The green number, green color. No, green color is just the second level. It's not the physical address. Right now, I'm just going to get the physical address all once, right? So this is 0xFFF. All right. So let's say the page offset is 0xFFF, and over here in PTE4 is 0xbeef. What is my physical address? My physical address is whatever I found on that table, and then I plug in the page offset. So what should be my physical address? Yes. I'll first start with beef, right? And as I said, I plug in the page offset, which is this thing. So it's FFF. Now, is it more clear? That's how I can find my physical address. Is it simple? Is this simple? Literally, from the virtual address, if you have the page table, which in this case the OS has one, right? You can then trigger the page walk process. You look at whatever goes into the first index bit. That tells you what row you're trying to access in this page, first level page table. Then it points to the location of the second level page table. You look at the index bit that points to whatever row you're trying to access, which then points to your physical address, right? Which then points to your physical address. All right, so that's 2-level, right? 32-bit 2-level. Page offset, as I said, just plug in whatever value you go in there, plug in the page offset. In the CPU you use nowadays, you have 64-bit. You have 64-bit. So basically now the virtual address is broken down into the offsets are the same, the last 12 bits. But then the rest are divided into chunks. Each chunk is 9 bits, right? Yes, 4 table. There will be a special register. This is a special register. I cannot write. I hate PowerPoint when it does this to me. It's a special. It's called CR3. The purpose of the CR3 is so that you can point to the first level table. It just tells me that's the address of the first level table. Then you use whatever is going to the leftmost side of your the virtual address to tell what row you're trying to access. And the level 4 page table entry would tell me the level 3 page table. So this level 4 page table, level 3 page table, right? Then you use the next set of bits to tell, okay, I'm going to this row in the next table, which would give me the next level 2 page table, right? Then I use the index for the next row, which again would give me, well, in this case, I kind of want to zoom in this part a little bit because now you have the physical frame number, which tell you the next table, right? Basically, it will tell you the next table, but then it actually now start to add the status bit, right? The metadata bit will tell you some status of the page, who owns it, how many times have I accessed it. If I want to kick this thing to the hard drive, should I do that because no one accessed this for a while, or should I do that later because I just accessed this? Then you use this again, PTE, right, would give you the location, the beginning of this page table. Then you use the last index again to figure out the physical page number along with the permission bits. Again, permission bits, think of it as a protection bit. It gives you protection against illegal access. Your physical address, right? Your physical address is basically this offset goes in here. This physical page number goes in here. PPN and page offset. Simple, right? Simple. And that's your 64-bit version. This is basically what gets used on your CPU nowadays, right now. All right. Now let's talk about protection a little bit, the permission bit. So the permission bits would give you something that you might have saw, right? So this is an example that Ajahn Piti posted on Facebook when he ran into this problem. So I'm going to show you an image. I got his permission to do this. So he was coding on his machine, and then suddenly, right, it crashed and say your computer was restarted because of the problem. And you look at the comments. If you zoom in there, right, debugger message, panic, you see some error status. You see this? What is that? Anything we just saw earlier from our lecture here. Page table entry. Now you actually got the page table entry, right? And it does have status that say, hey, the program is trying to access certain things, but you got invalid exception. So what does the OS do? It looks unsafe, so let me reboot, right? So that's what happened when you have things like protection bit. Basically, it allows something that could have done something bad from the access. Over here, see another thing that's familiar with. This is the MMU, Memory Management Unit, on the M1 chip, right? On the M1 chip, sorry, on the M1 chip. Basically, the Memory Management Unit found something that looks illegal, but it's not sure what it's supposed to do. So it just crashed itself and reboot. Right? So that is something that's part of the job of this protection bits. It allows you to ensure that every single memory access is safe, right? But then again, we now have to talk about performance because who doesn't want your computer to be fast? So let me ask you this question. Where is the page table? Where is the page table? DRAM. You got it right. Page table is in DRAM. And recall from our caching lectures, accessing DRAM takes a long time. Right? Accessing DRAM takes a long time. And let's say you have to do a 64-bit version, right? To get to my physical address, how many access to DRAM do I have to do until I got my physical address? How many trips do I have to go to DRAM? I have 4 levels of the page table. So how many trips do I have to go to DRAM just to get my physical address? To get my physical address, 4, and then to get to my data, that's the 5th access, right? So 5 trips to DRAM. That's bad. That's bad. That's never something we want to do, right? That's never something we want to do. So virtual memory as you design it come at a cost. And the cost is performance overhead. So now let's talk about how to get rid of it, right? So if you have 4 levels of the page table, you need to access memory 4 times until you know the address. So the first problem is I can't go to DRAM without knowing the physical address. So every single pointer access that I have, any access to an array in C, any access to a data in Python, any access to a data in Rust, for DRAM access just to know the physical address. Now that I know the physical address, what if my data is in the cache? What if my data is in the cache? Oh, it can get faster, but imagine we use address for the cache, right? But I never told you, is that virtual address or physical address, right? I never told you is that physical address or virtual address. So which one should it be? Which one should it be? Because the cache you need an address, right? For the cache, for the tags and the index bits. But I never tell you, is that physical address or virtual address? So let's say that's a physical address. What does it mean? To go to the cache, how many trips to DRAM do I have to do? Just to get to the cache. If I need the physical address to figure out the tag bits and the index bits, it means that I need to go to DRAM 4 times just to save the last trip to DRAM, right? So that's the second problem. We're not going to talk now. Sorry, now. In many modern design, you cannot access the cache without knowing the physical address. So let's tackle the first problem now, right? Now that you learn caching, what's the one quick thing we can do to fix the first problem? Now that you learn the technique called caching, the cache that we learned last week is there to store your data, right? So what else can the cache store? You can use something that looks like a cache, right? To store your physical address. That thing is called translation look-aside buffer, or the TLB. That's a cache. That's a cache for translation data. So now you know that virtual page number get translated to physical page number, right? So what I need to do is I build a cache that store physical page number, and I use the virtual page number as a way to look up my physical page number, right? So for a commonly used address, I'll put that in the TLB so that you can look up the physical address for any frequently used virtual address. This is going to behave like a cache, right? And there can be multiple levels of the TLB. On your machine, it might be L1 TLB, that is small, right? That every single CPU core have one, and then a much larger shared L2 TLB, right? And you only have to do the page walk. If your data is not in the TLB. All right. And now you start to see, once you know how things work, right, you can start to derive solution to certain problems. And here's the TLB structure, right? I want to use VPN as the key. And I want to use the VPN to find my physical page number. And that's all. VPN 10 can store VPN of 101, I don't know, like 11, 12, 21, 27. Or you can have a different VPN, right? Right. So basically, it's just giving you the mapping between VPN to PPN. Why is this enough? Why don't I need to store the virtual address, right? Because now I have the virtual address that looks like this: page offset and VPN. And then what I need is that translation into, right? Red is physical address, right? I need PPN. And then the rest of the physical address, right, it's basically going from the page offset. So I don't need the entire thing. I just need PPN. All right. Any question about this? Any question about this? Basically, we built a cache, but instead of caching the data, now we cache the mapping. Okay, so now let's move to the last thing we need to talk about today. Move to the last thing we talk about today. So the table is storing, no, this is actually on chip cache, which is SRAM. This is fast. So TLB use SRAM, not DRAM, and it's on chip next to the CPU, and they're really fast. So that's why you can quickly doing. Yes, it's basically one level table that gives you the mapping directly. Yep. And then because we use SRAM for that, it's really fast. All right. So now we tackle the first problem. The second problem is if you need to access the data cache, you need to know the physical address. Why? Now let's talk about why first. Let's talk about the why question. Okay. What do we need in a cache? We need the tag bits and we need the index bits, right? So your address will look like this. Tag, index, and then the byte and block, right? So basically this means that, and the same address can also be the virtual page number in page offset or physical page number in page offset, right? But given this, let me ask you this question. I have the index bit and have the tag bits. It means that I can use either of them for the index and the tags, right? Which means I have 4 choices. Which means I have 4 different choices. I can have everything is a physical address. I use physically address, physically index, physically tag. I can use physically index, virtually tag. I can use virtually index, physically tag, and I can use everything virtual address, virtually index, virtually tag. Right? Again, I'm just populating all the possible options. There's nothing complicated here except just a bunch of words here, right? I can use virtual address for either the index bit and the tag bit. The same goes for the physical address. So now I have 4 options. Now, because virtual address is just some fake address, so we can run into the problem where I have two programs that have the same virtual address, but they actually map to 2 different locations, 2 different PA, right? This is called homonym. And what you need is that the tag has to be able to tell the difference between the two, right? Because the tag is what you use to figure out, do I have a match or not? So just from this alone, right? Do I use physical address for the tag, or do I use the virtual address for the tag? We need physical address for the tag, right? So now our conclusion, PA is needed for the tag. All right, with me so far. So now let's go back to the four options we have, right? We just develop the thesis that we need physical address for the tag. So basically, this is not good. This is not good because otherwise we can have the problem where I have two the same virtual address from two different programs just happen to have the same virtual address. So I can't use virtual address for the tag. I need to use physical address for the tag. Now we have two choices. Let's talk about the trade-off. Let's have them fight between PIPT and VIPT. How many people guess PIPT wins? Okay, let's have a vote. All right, let's have a vote right now. I'm gonna open up the vote and see. You can just throw a random guess. There's no judgment on this at all because I haven't really like talk about which one is better. So PIPT versus PIPT. What is better? Add a poll, PIPT. Done. All right, just for fun, because we have a little bit of time left, open poll, go ahead and vote. And assuming that you guys are still trying to learn this, I was expecting that it's going to be kind of equal result, which is indeed looks equal. All right. By the way, awesome. Everyone participated. A few you haven't voted yet, so let's close the poll in 7 seconds. I'll give you 1 minute total to vote. Just for fun. Anyway, I just want to make sure that you're still awake. All right, let's close the poll right now, right? 10 versus 7. So just for fun, vote, right? So if we go by democracy, you guys are correct. This is indeed better, but now because we are scientists, right? Well, to be honest, we were being trained to be a good scientist. We should figure out why, right? So let's go with the issue with PIPT. Issue with PIPT. Basically, if I use PIPT, it means I need physical address for everything, right? So let me ask you this question. If I need physical address for everything, what is the first structure that I have to access before even going to the cache? That table, right? So you have virtual address, you then first have to go to the TLB, right? Hopefully you get physical address out of it, right? Then you go to the cache. So that's the problem because you need to get the physical address, right? So it's kind of slow. So if this thing somehow is like, say, spending 2 cycles there, and the cache access is 3 cycles, so now every single data access, if it hit in the TLB and hit in the cache, how many cycles do I have to spend to get my data in the cache? This is 5 cycle, right? Total. Not cool. Seems small, but not cool, right? Because you first need to go to the TLB. Now let's look at VIPT. Right? So obviously, you can finalize all the steps when you go to the cache. and then you have to need the physical address, which means you have to access TLB, right? So now you have the virtual address, and for sure you need to go to the TLB. And let's say this takes 2 cycles, right? Now, can I start going to the cache using the virtual address? What does the index bit give you? What does the index bit give you? Virtual address for the index bits and physical address for the tag bits. Index give me the cache set, right? So in the meantime, while I'm trying to check paste my address in the TLB, I can use part of the virtual address to go to the cache, right? In order to get my cache set, now you have the physical address, and this is just to compare the tag, right? So let's say this take also 2 cycles, and this is 1 cycle to compare all the tags, right? So how much time do I have to spend in this process? 3, yes, 3 cycles total, right? We just save a lot of time. We save almost 2x. We just get 40%. Oh, what's the speed up? It's basically we cut 2 cycles from it, right? 66% speed up. The cache lookup it can be done using the index bit from the virtual address, right? Why is this okay? Because we have the virtual address, we just go and get the cache set. In the meantime, you use the virtual address, go to the TLB to get the tag. Once you have the tag, you can then overlap, right? This allow you the overlapping process of I can go do some part of the lookup. In the meantime, I'll check the TLB. Then after I have the physical address, I do the tag checking. So we cut down from 5 cycles down to 3 cycles, right? 40% faster, right? We just saved 2 cycles. Well, the only downside, you want to make sure that thing is in the TLB, right? That's all. So TLB is really, really, really important. So one of the key takeaways here is the TLB is really important. Now let me wrap up everything from the caching lecture to the virtual memory lecture, because by this time, I believe many of you might be confused. So I'm gonna draw this diagram. I have my DRAM right here, right? I have DRAM right here. On the processor side, right? I can have the caching structure and the translation structure. The task of the translation structure is I want VA to be translated into PA. Caching structure is I just need my data, right? The caching structure basically have multiple levels of the cache. The translation structure has the TLB and the MMU, right? Now you have the load address, something like A equals star P, right? P is an address, and I want to figure out whatever P points to, put that in A. That's a load instruction, right? So now P is an address. Anything that's an address in the virtual world, I'll use the text, the red ink from here. P is an address, right? This is the virtual address. Virtual address will have VPN and the page offset. All right, with me so far. This is a virtual address that has the VPN, the page offset. And this same address, there's some index bit here that I can use to check the cache. I use the index bit from my virtual address to check the cache. Then I use the VPN. I use the VPN to go to the TLB, right? So if I have a hit in the TLB, what do I do next? If I hit in the TLB, what do I do next? I got the tag, right? Basically, the physical address becomes the tag, and I just check the L1 cache. But if my physical address is not there, what's the next step? What's the next step? If I don't have the address, then, well, if I don't have the address in the TLB, if I miss in the TLB, you do page walk. Yes, thank you. So you perform the page walk, which means you have to go to the page table multiple times, right? To get the tag. Now that you have the physical address, finally now you can check the cache. If it's not in the cache, right, you go and check the next level, and the next level, then you go to DRAM. And that's when you have the data. All right? Any questions so far? Any questions so far? Now that you have everything, right? Your physical address is just PPN and the page offset. TLB is in the same like close location. It's not a part of the cache. So cache here is used to store an actual data, right? And the TLB is there to store the translation. We use the same material for the TLB. The same material that we use for the cache, we also use that same material for the TLB, which is SRAM. It's on your CPU. Basically, when you buy an i9 processor, i3 processor, you got the TLB on it. Yeah. So basically, it's on the chip, right? Everything here is on your CPU. Anything here, this is on your CPU. All right. Hopefully that clears things out. Anything to the left side, not marked by DRAM, these are on your CPU. CPU would have, when you buy that chip, it has a processing core, and it has the caching. It has the cache, it has the TLB, right? It has the MMU that can do the page walk, and a way to work with the OS to perform the page walk. So one quick conclusion of this is all this structure, right, is there to make sure data access is fast. All right. Any last minute question before I go to the last concept, which is page fault? Oh, great question. Right. This is an awesome question because right now the research community is also looking into like, does that tree-like structure make sense? Like one giant table can work too, right? But it also means that now your table is either huge, right? Or you cannot support a lot of memory addresses. When you have these multiple levels of the table, it means that each level you can spawn into uh, like different pages, and you don't have to make such a huge total space for all your page table. Because imagine if you need to build a huge giant table for every single location DRAM, right? That table is likely to be big. Your page table doesn't have to be as big, and it's also more flexible. You need to support more than just whatever your DRAM cover. You can do that with the tree structure too. That's why it go full level, right? Because now you need to cover a lot of addresses. Because now these days your DRAM is big, right? Your DRAM is big. So the table structure make it more compact and also easy enough to like go through the table structure. Right? So a huge table would be the fast lookup solution, but it's not a viable solution yet because now your DRAM is really big. So great question. Hopefully that makes it a little bit more clear for you in terms of that particular question. Page fault is the last thing we have to, but that I aim to cover for this semester, right? Sometimes your address is not in DRAM, it's now get kicked off into storage. We call this page fault. When your data is actually no longer in DRAM, because the DRAM is full, it got put on the hard drive. The remedy here is basically you now have to perform the page fault process to get the data from storage, and that can take a lot of time, right? And again, the last thing, memory protection, right? Translation can utilize the access checking and see if things are valid or not. Otherwise, you get segfault. PTE would contain permission bits to make sure that you don't have any access violations, right? It can be things like address space ID, read-write, read-only bits, or user supervisor bit. All right, that's all. Before we leave today, any question about assignment 5? Because otherwise, for Thursday, we'll talk about the new in class. This would give you the material to practice for virtual memory lecture. We'll talk about assignment 5. And we also talk about, don't forget, we have the sample final. So if you have any question about these things, I haven't posted yet, it will be posted. Can we use late? No, that's the last possible day that I can humanely grade before OAA yell at me that I submit the grade late. Sorry, that's like the last possible day. That's really is the last possible day. So you cannot use the late token for A5 if you use it already. Oh, that's true. How should I fix this? I'm sorry. How can I make life a little bit better for you? I'm sorry about that. Oh, yeah, that's the last day I can viably put it, right? In class 9 due today, yes, A4 and in class. The other in class that's coming out, there'll be one, I think the one due in class 10, I think to Thursday, and then another in class basically before the final exam, because I want you to make sure you got through that before the final exam. Well, the purpose is so that you look at it like confused and then you ask us what's going on. All right. Because if you got confused during the final exam period and you ask us what's going on, I cannot answer. Final 21st, yes, same style as midterm. But again, no programming questions. Topics for the final is anything after the midterm, data representation, program representation, assembly, x86, caching, and virtual memory. Yes, I will go there and check it. All right. So I think that's all for today's lecture. We'll see you guys on Thursday. It should be a pretty like Q&A and really light session. We'll talk about any question you might ever have for the class, including assignments. Yeah, I think that's all. Enjoy the next class, and then we'll see you guys on Thursday. All right. Thank you so much for being here today.